Okay, welcome back. Hello everyone, I'm your friend in Saxo. Today we are going to learn the exponents and radicals.
Let's get some practice with our exponent properties, especially when we have integer exponents. So let's think about what 4 to the negative 3 times 4 to the 5th power is going to be equal to. And I encourage you to pause the video and think about it on your own. Well, there's a couple of ways to do this. One, you say, oh, look, I'm multiplying two things that have the same base. So this is going to be that base, 4, and then I add the exponents, 4 to the negative 3 plus 5 power, which is equal to 4 to the 2nd power. And that's just a straightforward exponent property. But you can also think about, why does that actually make sense? 4 to the negative 3 power, that is 1 over 4 to the 3rd power. Or you could view that as 1 over 4 times 4 times 4. And then 4 to the 5th, that's 5 4s being multiplied together. So it's times 4 times 4 times 4 times 4 times 4. And so notice, when you multiply this out, you're going to have 5 4s in the numerator and 3 4s in the denominator. And so 3 of these in the denominator are going to cancel out with 3 of these in the numerator. And so you're going to be left with 5 minus 3, or negative 3 plus 5 4s. So this 4 times 4 is the same thing as 4 squared. Now let's do one with variables. So let's say that you have a to the negative 4th power times a to the, let's say, a squared. What is that going to be? Well, once again, you have the same base. In this case, it's a. And since I'm multiplying them, you can just add the exponents. So it's going to be a to the negative 4 plus 2 power, which is equal to a to the negative 2 power. And once again, it should make sense. This right over here, that is 1 over a times a times a times a. And then this is times a times a. So that cancels with that cancels with that, and you're still left with 1 over a times a, which is the same thing as a to the negative 2 power. Now let's do it with some quotients. So what if I were to ask you, what is 12 to the negative 7 divided by 12 to the negative 5 power? Well, when you're dividing, you subtract exponents if you have the same base. So this is going to be equal to 12 to the negative 7 minus negative 5 power. You're subtracting the bottom exponent. And so this is going to be equal to 12 to the, subtracting a negative is the same thing as adding the positive, a 12 to the negative 2 power. And once again, we just have to think about, why does this actually make sense? Well, you can actually rewrite this. 12 to the negative 7 divided by 12 to the negative 5, that's the same thing as 12 to the negative 7 times 12 to the 5th power. If we take the reciprocal of this right over here, you would make the exponent positive. And then you get exactly what we were doing in those previous examples with products. And so let's just do one more with variables for good measure. Let's say I have x to the negative 20th power divided by x to the 5th power. Well, once again, we have the same base, and we're taking a quotient. So this is going to be x to the negative 20 minus 5, because we have this one right over here in the denominator. So this is going to be equal to x to the negative 25th power. And once again, you could view our original expression as x to the negative 20th. And having an x to the 5th in the denominator, dividing by x to the 5th, is the same thing as multiplying by x to the negative 5. And so here, you just add the exponents, and once again, you would get x to the negative 25th power.
Okay, I don't know if you have ever learned something from this video, but I'm going to tell you.
By x to the 5th.
It's quite simple. Now, when you divide two numbers, which they both have the power component, then you minus the component. The upside one minus the downside one. But when you multiply two numbers, which then both have the power component, then what you're going to do is to keep the base number. Well, add the two component number together. Example for this case, -7 plus 5. Well, in real life, you don't necessarily have to calculate this number by yourself, because I guess for most of the cases, the calculator would, or the computer would do that job for us.
And then taking the product. So this is going to do some example raising exponents or products of exponents to various powers, especially when we're dealing with integer exponents. So let's say we have 3 to the -8 times 7 to the third, and we want to raise that to the -2 power. And I want you to pause this video and see if you could simplify this on your own. So the key realization here, there's a couple of ways that you can tackle it, but the key thing to realize is if you have the product of two things and then you're raising that to some type of a exponent, that is going to be the same thing as raising each of these things to that exponent and then taking the product. So this is going to be the same thing as 3 to the -8 and then that to the -2 times 7 to the third to the -2. So I'll do 7 to the third right over here. And now if I want to simplify this, 3 to the -8 to the -2, we have the other exponent property that if you're raising to an exponent and then raising that whole thing to another exponent, then you can just multiply the exponents. So this is going to be 3 to the -8 times -2 power. Well, -8 times -2 is positive 16. So this is going to be 3 to the 16th power right over there. And then this part right over here, 7 to the third to the -2, that's going to be 7 to the 3 times -2, which is 7 to the -6th power. So that is 7 to the -6. And this would be about as much as you could simplify it. You could rewrite it different ways. 7 to the -6 is the same thing as 1 over 7 to the 6th. So you could write it like 3 to the 16th. Let me use that same shade of blue. 3 to the 16th over 7 to the 6th. But these two are equivalent. And there's other ways that you could have tackled this. You could have said that this original thing right over here, this is the same thing as 3 to the -8 is the same thing as 1 over 3 to the 8th. So you could have said this is the same thing as 7 to the third over 3 to the 8th. And then you're raising that to the -2, in which case you would raise this numerator to the -2 and the denominator to -2, but you would have gotten to the exact same place. Let's do another one of these. So let's say that we have got a to the -2 times 8 to the 7th power, and we want to raise all of that to the 2nd power. Well, like before, I can raise each of these things to the 2nd power. So this is the same thing as a to the -2 to the 2nd power times this thing to the 2nd power, 8 to the 7th to the 2nd power. And then here, -2 times 2 is -4. So that's a to the -4 times 8 to the 7 times 2 is 14. 8 to the 14th power. In other videos, we go into more depth about why this should hopefully make intuitive sense. Here you have 8 to the 7th times 8 to the 7th. Well, you would then add the two exponents, and you would get to 8 to the 14th. So however many times you have 8 to the 7th, you would just keep adding the exponents, or you would multiply by 7 that many times. Hopefully that didn't sound too confusing. But the general idea is if you raise something to an exponent and then another exponent, you can multiply those exponents. Let's do one more example where we are dealing with quotients, which that first example could have even been perceived as. So let's say we have 2 to the -10 divided by 4 squared, and we're going to raise all of that to the 7th power. Well, this is equivalent to 2 to the -10 raised to the 7th power over 4 squared raised to the 7th power. So if you have the difference of two things and you're raising it to some power, that's the same thing as the numerator raised to that power divided by the denominator raised to that power. Well, what's our numerator going to be? Well, we've done this drill before. It'd be 2 to the negative 10 times 7th power. So this would be equal to 2 to the negative 70th power. And then in the denominator, 4 to the 2nd power. Then that raised to the 7th power. Well, 2 times 7 is 14. So that's going to be 4 to the 17th, 4 to the 17th power. Now, we actually could think about simplifying this even more. There's multiple ways that you could rewrite this. But one thing you could do is say, hey, look, 4 is a power of 2. So you could rewrite this as this is equal to 2 to the negative 70th power over, instead of writing 4 to the 17th power, why did I write 17th power? It should be 4 to the 14th power. Let me correct that. Instead of writing 4 to the 14th power, I instead could write, so this is 2, let me get the colors right. This is 2 to the negative 70th over, instead of writing 4, I could write 2 squared to the 14th power. 4 is the same thing as 2 squared. And so now I can rewrite this whole thing as 2 to the negative 70th power over, well, 2 to the 2nd, and then that to the 14th. Well, that's 2 to the 28th power. 2 to the 28th power. And so can I simplify this even more? Well, this is going to be equal to 2 to the, I can just, if I'm taking a quotient with the same base, I can subtract the exponent. So it's going to be negative 70. It's going to be negative 70 minus 28th power. Minus 28. And so this is going to simplify 2 to the negative 98th power.
Okay, that makes sense. So what do they call the, let me do a drawing here. What do they call a number like this? They call it exponent, right? And what do they call this behavior? They call it quotation. And what do they call this kind of behavior or operator? They call it products. Okay, and for each, let's say, operation, the power number would behave differently. For example, for this one, you just have to multiply the power number together. And for, let's say, for this from, you just have to minus the power number. Anyway, it's quite, let's say, it's quite obvious that if you have a common base for your exponents, you could do that kind of operation without any problem. Yeah, let's go to another idea called radicals. Radicals. All right.
5 squared. If you're watching a movie and someone is attempting to do fancy mathematics on a chalkboard, you'll almost always see a symbol that looks like this radical symbol. And this is used to the square root, and we'll see other types of roots as well. But your question is, well, what does this thing actually mean? And now that we know a little bit about exponents, we'll see that the square root symbol or the root symbol or the radical is not so hard to understand. So let's start with an example. So we know that 3 to the 2nd power is what? 3 squared is what? Well, that's the same thing as 3 times 3. That's going to be equal to 9. But what if we went the other way around? What if we started with a 9 and we said, well, what times itself is equal to 9? We already know that answer is 3, but how could we use a symbol that tells us that? So, well, as you can imagine, that symbol is going to be the radical here. So we could write the square root of 9. And when you look at this way, you say, okay, what squared is equal to 9? And you would say, well, this is going to be equal to 3. And I want you to really look at these two equations right over here, because this is the essence of the square root symbol. If you say the square root of 9, you're saying what times itself is equal to 9? And, well, that's going to be 3. And 3 squared is equal to 9. I can do that again. I can do that many times. I can write 4 squared is equal to 16. Well, what's the square root of 16 going to be? Well, it's going to be equal to 4. Let me do it again. And actually, let me start with the square root. What is the square root of 25 going to be? Well, this is the number that times itself is going to be equal to 25, or the number where if I were to square it, I get to 25. Well, what number is that? Well, that's going to be equal to 5. Why? Because we know that 5 squared is equal to 25. Now, I know that there's a nagging feeling that some of you might be having, because if I were to take negative 3 and square it, I would also get positive 9. And the same thing, if I were to take negative 4 and I were to square the whole thing, I would also get positive 16, or negative 5, and if I were to square it, I would also get positive 25. So why couldn't this thing right over here, why can't this square root be positive 3 or negative 3? Well, depending on who you talk to, that's actually a reasonable thing to think about. But when you see a radical symbol like this, people usually call this the principal root. Principal square root. And another way to think about it, it's the positive. This is going to be the positive square root. If someone wants the negative square root of 9, they might say something like this. They might say the negative. Let me scroll up a little bit. They might say something like the negative square root of 9. Well, that's going to be equal to negative 3. And what's interesting about this is, well, if you square both sides of this equation, if you were to square both sides of this equation, what do you get? Well, anything negative squared becomes a positive. And then the square root of 9 squared, well, that's just going to be 9. And on the right-hand side, negative 3 squared, well, negative 3 times negative 3 is positive 9. So it all works out. 9 is equal to 9. And so this is an interesting thing. Actually, let me write this a little bit more algebraically now. If we were to write the principal root of 9 is equal to x. There's only one possible x here that satisfies it, because the standard convention, what most mathematicians have agreed to view this radical symbol as, is that this is the principal square root. This is the positive square root. So there's only one x here. There's only one x that would satisfy this, and that is x is equal to 3. Now, if I were to write x squared is equal to 9, now this is slightly different. X equals 3 definitely satisfies this. This could be x equals 3, but the other x that satisfies this is x could also be equal to negative 3, because negative 3 squared is also equal to 9. So these two statements are almost equivalent. Although when you're looking at this one, there's 2 x's that satisfy this one, while there's only 1 x that satisfies this one, because this is the positive square root. If people wanted to write something equivalent where you would have 2 x's that could satisfy it, you might see something like this. Plus or minus square root of 9 is equal to x. And now x could take on positive 3 or negative 3.
All right, interesting. That's how they call the radicals or square roots, or something like that. Okay, let's have a look at the fifth roots, because it's just a general idea about the roots.
The fifth root of 32. So like always, pause the video and see if you can figure this out on your own. So let's just remind ourselves what a fifth root is. So if x is equal to the fifth root of 32, that's the same thing as saying that x to the fifth power is equal to 32. So we have to find some number where if you take 5 of them and multiply them together, that you get 32. So there's a couple of ways to approach it, especially when you're doing with these really higher order roots here. So let me rewrite the fifth root of 32 here. One way is you could try to factor 32 and see are there factors that show up 5 times? And so 32 you might immediately recognize as an even number, so it's going to be divisible by 2. It's 2 times 16. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. So in this case, doing the factoring technique worked out well, because we see that this is 2 times 2 times 2 times 2 times 2, or 2 to the 5th power. You could rewrite this as the 5th root of 2 to the 5th power, which is, of course, going to be equal to 2. 2 to the 5th power is 32. Now let's do another one. This is going to be a little bit harder. All right. Let's say we want to take the 5th root of 243. So now a much, much larger number. So there's a couple of ways to do this. One, you could try the factoring, although that's going to be harder now that it's a larger number. Or you could do a little bit of trial and error. Doing higher roots without the aid of some type of calculator or something gets a little bit more complicated. So here, if we wanted to do the factoring technique, we could say, all right, it's not divisible by 2. I like to start with the smallest possible factor. So it's not divisible by 2. Is it divisible by 3? And you might be familiar with the test to see if something is divisible by 3. You add up the digits and see if that sum of the digits is divisible by 3. So if I were to take 2 plus 4 plus 3, that is equal to 9. And so it is divisible by 3. So this is going to be equal to 3 times, let's see, 3 goes into 240 80 times, and then 1. So 81 times. And so 81 is also divisible by 3. I have a sense of where this is going now. It's 3 times 27, which is 3 times 9, which is 3 times 3. So using the factoring method, we're able to see that 3 to the 5th power is 243. So the 5th root of 243 is equal to 3. Now, another way that you could have done it is a little bit of trial and error. We already know, well, we know that 1 to the 5th power is just going to be 1. We know that 2 to the 5th power, we just calculated that, that's 32. Well, we now know what 3 to the 5th is, but let's say we're just trying to zoom in on it a little bit. So let's say if you wanted to see what 4 to the 5th is, well, that would be 4 times 4 times 4 times 4 times 4. So let's see, this is going to be 16. 16 times 4 is 64, times 4 is 256, and then that times 4, and I just happen to know this, but you might want to do it by hand, this is 10,024. So if you're taking the cube root of 243, you're saying, hey, what to the 5th power? Something to the 5th power is equal to 243. And if you have a sense that it's going to be an integer solution, if you think it's going to be something like a 2 or a 3, well then 3 is probably going to be a good guess here. If the possible answers are going to be decimals, then it's going to be a lot more complicated. But that's another way to say, hey, maybe I'll try out 3. And if you tried out 3, you would get 243.
Okay. So to be honest, we couldn't.
And if you have a sense that it's going to be
we couldn't just go on and directly calculate the answer of this equation, right? That's so sad. But here's the good news. You can also use the computer to help you calculate that value. Because to be honest, this kind of calculation process is it's quite feasible for a computer, but not for human, because if you do it by human hand, it's gonna take a lot of time, and human probably would make some mistakes when they do it. Okay, let's go to the next topic, simplifying square roots.
Let's see if we can simplify 5 times the square root of 117. 117. So 117 doesn't jump out at me as some type of a perfect square. So let's actually take its prime factorization and see if any of those prime factors show up more than once. So it's clearly it's an odd number. It's clearly not divisible by 2. To test whether it's divisible by 3, we can add up all of the digits, and we explain why this works in another place on Khan Academy. But if you add up all the digits, you get a 9. And 9 is divisible by 3, so 117 is going to be divisible by 3. Now let's do a little aside here to figure out what 117 divided by 3 actually is. So 3 doesn't go into 1. It does go into 11 3 times. 3 times 3 is 9. Subtract. You got a remainder of 2. Bring down a 7. 3 times, okay, 3 goes into 27 9 times. 9 times 3 is 27. Subtract and you're done. It goes in perfectly. And so we can factor 117 as 3 times 39. Now 39 we can factor as, that jumps out more at us, that's divisible by 3. That's equivalent to 3 times 13, and then all of these are now prime numbers. So we could say that this thing is the same as 5 times the square root of 3 times 3, 3 times 3, 3 times 3 times 13, times 13. And this is going to be the same thing as, and we know this from our exponent properties, as 5 times the square root of 3 times 3, 5 times the square root of 3 times 3, times the square root of 13. Now, what's the square root of 3 times 3? Well, that's the square root of 9. That's the square root of 3 squared. Any of those, well, that's just going to give you 3. So this is just going to simplify to 3. So this whole thing is 5 times 3 times the square root of 13. So this part right over here would give us 15 times the square root of 13. Let's do one more example here. So let's try to simplify 3 times the square root of 26. Actually, 26 in yellow like I did in the previous problem. 26. Well, 26 is clearly an even number, so it's going to be divisible by 2. We can rewrite it as 2 times 13. And then we're done. 13 is a prime number. We can't factor this anymore. And so 26 doesn't have any perfect squares in it. It's not like we can factor it out as a factor of some other numbers and some perfect squares like we did here. 117 is 13 times 9. It's the product of a perfect square and 13. 26 isn't. So we've simplified this about as much as we can. We would just leave this as 3 times the square root of 26. We would just leave this.
Okay, the most valuable lesson that we have learned for this video, that we can learn from this video, is that for this equation, we speak it with 3 times the square root of 26. Let me just listen to it again.
This as 3 times the square root of 26.
Alright, let me just read it again. 3 times the square root of 26. 3 times the square root of 26. Why I think this kind of practice is very important? Well, it's just because if you cannot if you cannot speak it out, then you won't remember anything. You'll remember a bunch of tedious and boring symbols in your mind, but you cannot explain it to other people. So other people would never know what kind of thing that stones in your hand. That's too bad. Alright, I guess that's the end of this lesson, and inside of this video we have learned about the concept of exponents, and we have learned the idea of radicals. In other words, the radical also called the square root, but it can be more, for example 5 roots or 6 roots or infinity roots. Alright, that's today's learning, and I hope you enjoy it. I'll see you guys in the next video. Bye!